Welcome, everyone. Thanks for joining us, those of you in the room and those of you online. My name is Carl Dobman, and I'm the Dean of the College of Architecture and Design at LTU. It's exciting to have Shawn Keller with us today in person. Our lectures are carefully curated to find great speakers who can speak to the concerns of many different degrees within our college. We offer professional design degrees in architecture, interiors, graphic design, game design, industrial design, and transportation design. Shawn, with the work of CW Keller, engages issues clearly related to many of these different degrees. I also want to thank the Ford Fund for their support of this lecture, their continued support of our college, and their dedication to innovation in design and technology sectors. Their investment and work continues to strengthen our communities and support our educational institutions in these areas. Thank you, Ford Fund, for being such a great partner and helping us offer our students these types of engaging opportunities. We've all attended lectures, which we love, by designers. From their vantage point, we learn the intent and we often see the final outcome. I'm incredibly excited to have Shawn here with us today because I also love seeing behind the scenes, and that's what we're going to get a glimpse of today. I love photos from the fabrication floor and to see things happening. And for a long time within my own practice, we often joked that photos were always better with clamps in them, and I know that Shawn can do that too. We also know that the design industry needs creative and smart people in many different roles, and our students often end up in these different types of roles. Shawn's a perfect example. Designers are valuable throughout the design, construction, and manufacturing process. I've been aware of the work of CW Keller for a while through their collaborations on projects like Sea Change and Harbor Park Pavilion, where they demonstrate their amazing ability as craftspeople. I was blown away by their collaboration on the Alliance Theater with Matthias Plesnig and Tehran Architects, as well as Faro Technologies. In this project, there's an incredible craft advancement that brings together the skills of traditional woodworking with 3D scanning technology. This results in an incredible and complex millwork package completely prefabricated in their shops. So you can tell I'm really excited about these types of things. And it's because of this blend of old and new that results from an amazing technology infusion. This also aligns well with our ethos at LTU, a technological university where we teach students to critically and productively engage technologies to advance professional design practices. So a little bit about Shawn. Shawn Keller grew up in the fabrication industry. He received a BFA in interior design from Syracuse University. He's been part of CW Keller since its founding in 1974 and to his current role as president today. Shawn's leadership of the company draws upon his experience as a fabricator on the shop floor, his time as an architectural project manager, and his roles within CW Keller as project manager, engineer, and head of business development. Shawn is driven to build a company that exists as a crucial link between concept and making, and he'll be talking about that today. His strength is building connections between designers and makers by using technology as a language to illustrate and inform the decision-making process that is the path to successful projects. I want to thank Shawn for taking the time out of his busy schedule to join us here in Detroit and to be with us on campus. Help me welcome Shawn Keller.
Thank you, everyone. Give me 1 second for the laptop to wake back up. So Carl did half of my introduction there by telling you about me. Thanks for having me here today. I'm grateful for the opportunity and want to thank Andrea and Chris and Carl and Katie for making the connection. I was saying to them earlier, I often spend most of my time presenting and selling our company to clients and architects. And so It's fun to come into an environment like this and talk really from a different perspective. I'm not trying to sell you guys. I really want to talk to you about our company's experience over the past 47 years in learning to do projects that we think are some of the most complex in the industry and in the country. But I'm going to take a minute to step back. I did a little homework on LTU, and I'm going to borrow some language from your university collateral to get us started so we can tie things together here. So your school's mission is to develop innovative and agile leaders through a student-centric learning environment and applied research embracing theory and practice. And theory and practice is the part that I want you to remember because we're going to come back to that. Your university's values are character and integrity, theory and practice, teamwork and trust, and that's a huge one in the construction industry. You either have teamwork and trust or you don't, and many projects don't. But it's something that you, as the initiators of project, can set the tone for at a very powerful scale. And finally, the university's cause is the intellectual development and transformation of our students into critical thinkers, leaders, and lifelong learners. And lifelong learning is also a critical thing. And what I'm going to spend most of my day talking about, or most of the presentation talking about, is how our company's success is really tied to learning from others. We are really good collaborators. We don't know how to do everything that's involved in our projects, but we're really good at creating teams of people that do know how to do all the aspects of a project, and relying on their expertise to bring their profession and their skill set to the success of the project. The title of today's lecture is Melding of Digital Tools and Craft in Complex Fabrication. Simply saying we're going to talk about computers and software, technology, lots of lasers, as tools that have a significant value and contribution to construction. But we're also going to talk about clamps, lots of them, approximately 10,000 for the Alliance Theater, and sandpaper and ladders and glue and arms and legs and people, because while the fun side of learning about architecture and design is to look at what can a robot do, what can a 3D printer do, we are, as someone who's been in this industry for 30 years now, very far away from robots building our buildings. People build our buildings. And the digital tools that you all have at your disposal are going at a pace that is so different from the rest of the construction industry that they're starting to spread too far apart. And so I'm going to circle back to that in a second. So I'll do the abbreviated version because Carl gave you some of the background. My dad started the company in 1974 in the basement of our house. So I did literally grow up with CW Keller downstairs with bandsaws and table saws. He also went to Syracuse, worked for Gillette for a while, was an industrial arts teacher, and was making coffee tables and cutting boards and things in our basement and selling them. And that turned into someone's kitchen and then someone's office. And the stepping stones of a lot of woodworkers is growing from residential into commercial. Our company's big break was in the early 80s getting contracted to work for Estee Lauder. And so we had about a 15-year run of doing retail store fixtures on a nationwide basis for Estee Lauder. And that really allowed the company to grow and expand, build out the facility that we are in today, start to introduce CNC, start to move away from paper. And I will date myself, I started when I graduated from Syracuse still drafting by hand, to where we are today, which is a fully Rhino-based. We do a lot of work in SolidWorks. We do a lot of automation in Grasshopper, and a huge leap from where the company started. And it's really an embracing of that technology. And a lot of what we were doing is trying to keep up with Katie and keep up with others in the design world, because the pace that they were going is leaving a lot of the construction industry behind. When I graduated, I went to work for an architecture firm in Boston and was there for about 10 years. And what it gave me was a perspective that you all will have in working, if you go to work for firms, of, I'll call it the client side of the table. You're working directly with clients, and they've come to you and they've said, we want you to design this room for us. And everyone at that point in the project is in good spirits because your client hasn't spent any money yet, and you all get to design something fabulous for them. And everything's going to move forward and it's going to be wonderful. And what I learned after repeatedly making this mistake with our firm over and over and over again was we would constantly overpromise. We would design these wonderful environments and we'd get our client very excited about it, and then we would go to the dreaded general contractor. And the general contractor would get our drawings and they'd come back and they'd say, here's your budget to build this space. It's $1 million or $2 million or $500,000. It didn't matter what the number was. It was usually 2 times what we had told our client was going to cost. And that is a cycle that repeats itself every day across the country with design teams and contractors and clients. And it's something that I felt living through it so many times, there's got to be a better way to do this. Because when that happens, everybody's upset. Your client has bought into what you have designed for them. And now you have to go back and tell them that they can't have it. And your general contractor is already on the defensive because they are the bad guys who came to the table with, you don't have enough money to build your project. And you start what is called value engineering. And value engineering really just means get rid of all the good stuff. Just start scaling it back, delete the hanging system from the middle of the room, get rid of the lighting, get rid of that projector. You can't afford it. You never could afford it to begin with. And that process is one that fundamentally hurts all parties. Your client's not going to end up with what they hoped they were going to have. Architects are going to spend more time and money redesigning it to try to get it to a budget. And you're going to have this confrontational period of construction where you're always kind of looking at each other and wondering, why is this costing me so much? Is this person taking advantage of me? And so what we started to do, I'm going to go one slide back. When I went back to CW Keller, we really made a concerted effort to engage with design teams early. And you'll hear things like design assist, delegated design. It happens a lot with specialty fabricators. Glazing systems on buildings are either developed by engineering and architecture firms that just specialize in facade, or they're done by the facade manufacturers themselves. And the shift in the industry is to specialize. So firms like ours that specialize in complex fabrication become a part of project teams early on. And I'm going to give you all my phone number and my email address at the end of this. And I would encourage you to call me, call the people on my team, call other people that you meet in the industry and ask them, I've designed this beautiful thing. How much is it going to cost? How would you build it? What am I missing? What other people would need to be involved? If you ask those questions early, and you start to engage with industry, then you will engage in that lifelong learning that I'm talking about. And you will start to recognize and realize that the people who build these things have a really fundamental, there's a fundamental joy and excitement about building. And they want to share their information. I love coming and talking about the work that we do because it's beautiful and it's fun and it's cool. And so don't live in a vacuum. Engage with the people who build, whether that's the plumber, the electrician, the glazer, the roofer, the drywall guy, the carpet person, and engage with them early and avoid the need to value engineer. So going into the Alliance Theater. So I was going to use Alliance Theater as kind of the main topic of the presentation today to talk about all the things that they didn't do that I just explained at the beginning of the presentation, and then the process that we go through in trying to achieve and engineer and fabricate a really complex project. This was 250,000 linear feet of steam-bent white oak crafted to create essentially the interior of a world-class acoustic theater. So Trahan Architects was engaged by Coca-Cola and the Woodruff Art Center to redesign one of the performing arts theaters inside the Woodruff Art Center, which is a large, sprawling art campus. And so that honeymoon phase that I talked about, architect wins the award. Trahan is going to design the inside of this theater from scratch. And so they start in Rhino and start modeling away, and they create lots of straight lines, and they do a lot of analysis. And then they say, we need more geometry in this space. And then they say, straight's kind of boring. Let's really start to add curvature to the space. We need everything to flow through the environment. It's going to be more warm and inviting, and patrons are going to enjoy that more. And then if you've got single curvature, why don't we use double curvature? Because that's much more interesting than single curvature, and we need a lot more geometry in the space. And now we need the acoustician who's going to come in and say, well, you need transparent surfaces and you need reflective surfaces. So some of it can be lines and some of it has to be solid so that we reflect the sound back. And so Trahan keeps going and going and going, and for about a year works on the development of every aspect of the theater: lighting design, acoustical design, stage and theater, seating engineers, structural engineers, and gets to a place where they've designed the inside of the Alliance Theater. And if you're familiar with Matthias Plesnig, he's an artist in Brooklyn who builds handcrafted, steam-bent wood benches that are exquisite. And it takes him about 3 to 4 months to build one bench. So we extrapolate that out over the Alliance Theater, it would take Matthias about 11 years to build the inside of the theater. And so our firm was engaged to essentially be able to take the art of Matthias Plesnig's work and the design that Trahan Architects had developed and the acoustical qualities and the client's budget. And at the point that we were engaged, those things were very far apart from each other, and start to bring them together. And so how do we do that? How do we take a space that is that complicated? And it's the analogy that I used before. Okay, we've drawn it. How much does this cost? And we always say, well, how much do you think it's going to cost? Because I don't know how much that's going to cost. It took us 800 hours, man-hours, to do the initial bid, and about a year to get to the point where we had an approved budget to build it. And that was before we started the contract to actually build it. So for something this complicated, there's a huge investment of time, because if you get it wrong, it gets very expensive very quickly. And so that's where the digital side of our process really comes into play. And I'm going to talk about two folks in our team here. The first thing we did was, the other thing that the architect wanted to do was they wanted it to be seamless. No seams anywhere visible in the entire environment. So the wood slat that starts on this wall has to travel all the way around the room and end over there, and we don't want any seams in it. And we said, okay, well, how are we going to get it there? How are we going to build it and ship it? Well, we want to build it on site. And that's where we go back to, okay, well, it's going to take you about 11 years to do that. Because if we have to build it on site, we have to do it by hand. There's no way to actually do that. And that's the push and pull. That's where, when we talk about teamwork and trust as part of the mantra of this school, you have to engage in a back and forth with the people who are essentially engaged to make your project successful, and compromise. There are going to be times where you don't want to hear that you have to put seams in your space. We had to put a lot of seams into this space. And even there, the compromise we made was we were making balcony panels that were 27 feet long and ceiling panels that were 4,000 pounds to reduce the number of seams. And all of that costs money. That's all decisions that get made through the process of client interaction, architect, and fabricator to reach some compromise between anything's possible to what is practical and reasonable to make this project successful. And so our team engaged in a process of taking the design models and building what we call fabrication tolerance models, where we're going to engineer every aspect of the project. Every stringer, we call them, all 250,000 feet, was engineered to show where the seams were within each balcony rail, because wood, as a raw material, doesn't come 300 feet long, and our machines aren't 300 feet long. So we're taking sticks of wood that are 10 feet long or 12 feet long, and we have to join all of those together to create the assemblies that become wall panels and balcony rails. And so this was what Matthias had created as a mock-up that we then had to turn into a production, I'll call it a commercial scale production, to be able to build for the project. And so you can see, start to see some Matthias clamps. The way we do it is through developing a workflow and a process for fabrication, and really stitching together, and I'm going to use two people in our company, Greg and Paul. Greg is he is you guys. He is a mechanical engineer by training. He is super savvy in structural and engineering and scripting, and can turn the theater model into a production model. What Greg doesn't know is, how do you steam bend? How do you glue splice joints together? How much can I bend a piece of wood? And so Paul, who runs one of our teams on the floor, is the other half of that process. The two of them have to work together. And that's a fundamental success that I'll say we have in our company, is we force those generational differences. Paul is older, Greg is younger. Background differences. Paul never went to college, Greg obviously did. And we want them to work together, because when they do, the two of them together become so much more powerful in what we can accomplish as a fabricator. And so Greg and the team worked out how we are going to communicate to Paul what he has to build. And so think of a bowl of spaghetti. You're going to pull a noodle out, and you're going to perfectly place that noodle in the geometry that it needs to be in, 1/4 of an inch away from the other noodle, and let it sit there until it dries and hardens, and then move on to the next one. How do you know where to put it? You're not going to use a tape measure to measure this. You need some type of tool that is going to allow you to place this where it needs to be to create this sculptural surface. And so we worked through a process of building control surfaces and then extrapolating the geometry of every one of these lines, and then working with our fabrication team, said, okay, well, how are we going to build this? We need a jig. The jig is the most fundamental thing you will see in a woodworking shop. And it can be as simple as a little block that holds something against your bench, or as complicated as what we'll map out here. The jig is helping the team in the shop visualize and understand what they're actually building, because we're not using tape measures. There's no way to measure anything on the assembly of these. And so we engineered a jig system. It's a plate that shoots to the floor. It's vertical steel posts. We machine, so we engineer and design and cut and produce a plywood system that attaches to those steel posts. And we add machined geometry that we've extrapolated from the model that represents the curvature of what we're going to build. So now you can start to visualize what that balcony rail is going to get attached to be able to assemble it. And we add steel connectors, because at the end of the day, everything that you're seeing here currently goes away. None of it is part of the final assembly. It's only what we need to be able to build the assembly. And voila, you have the balcony rail. And obviously it's not nearly as simple as that. Because we need to figure out now how to build the back of the balcony rail, and the jig's in the way. And so you have to build another jig that allows you to take the first one out, support the outside face, so that you can then steam bend and build the inside face, because these are two-sided balcony rails. I'm sitting on one side, and the theater is exposed to the other side. And so there's Paul. He's on my left with the glasses. And that's the jig. You can see the steel posts in the background and the plywood. And what Ryan is doing on the right, and it's hard to see in the screen, there's little green lines at the top of the stringer or the vertical that he has his finger on. What we did was working with Autodesk and Faro Technologies. There is technology out there called 3D laser projection. And what it was originally used for was to project geometry on the outside of planes so that they could put the logos on the fuselage of a plane. And a plane is not a straight tube extrusion. It bellies out in the middle, and obviously it curves in section. And so to get the graphic on the plane and lay it out correctly, you project the lines on a 3D surface. And so what the technology is doing is you're modeling what you want to project, you're modeling what you want to project on, and then the laser will draw a 3D line on a 3D surface. And so that was the technology that we used for our team in the shop to understand how they were going to place the stringers that became spaced apart to become acoustically transparent and then all converge, and at what degree they converge and at what pace they converge. It was all done through laser projection. I kept this image on the right. People have asked me a million times if we were running like a toxic waste dump on the image on the right. What happens when you steam bend oak is it has metal content in it and mineral content in it. And when you steam it, all of that steam starts to pull those minerals out of it, and it turns the water black. So our shop floor, for about a year after finishing this project in this area, is all covered with black water. But those pink tubes that you're seeing are our homemade steam chambers. You essentially buy a steam unit that you would put in like a steam shower and build tanks that we can plug that into, and that's what you do to steam wood. You put the wood in and you let it sit in the steam at about 200 degrees, and you can take it out in about 30 minutes, maybe an hour or two based on the thickness of the wood, and you can literally bend it with your hands to conform to the shape of the piece that you're building. And so here's where we get into clamps. We had to purchase about, I think it was about 8,000 clamps, maybe not 10,000 clamps, because we had to build the entire theater at the same time. We couldn't build one and then the other and then the other. We had to be constantly building balcony components and shipping them to the job site. The other aspect of the job is machining. So we're crafting, we're building, we're assembling, we're also using our fabrication tolerance model to CNC machine. And I'm an advocate for CNCs. They're much more robust than robots. Robots have lots of tolerance issues when you start to put a lot of load at the end of a robot, so they're good for doing certain things. But if you're going to take a billet of MDF and machine inches of it away to create that shape, you really want the robustness of a CNC to be able to do that work. And so these are areas where we were machining solid billets of material to create acoustically reflective surfaces in the project. So going back to the process of the 3D projection, what is happening a lot in the industry, and you've probably heard about laser scanning, that's been around for a while, is the movement to, scanning is great. We have framed this room, we've not done any fishes, we're gonna come in and we're gonna scan it so that we can see, did it get built the way we anticipated? And then we can do tolerance analysis. 3D laser projection is taking that to the next step, where we can come into this room and we can laser project the location of that outlet. So the electrician knows where to put that outlet. They don't need drawings. It's all in the coordinated model. The projector is going to project the layout of these vent grills on the wall, or it's going to project the layout of those hanging points on the ceiling. It's coming. It sort of works, and you'll see as I get into some of these images. The other big disconnect that you're going to see in the construction industry, and I think we're going to talk about BIM this afternoon a little bit. BIM is awesome if we're all doing BIM. And if everyone on a project team is doing BIM and we're good at it, we all put our models in, then you're done with your model. I've got all the information I need. I never need to go to the job site because he modeled it. 80% of the trades can't do BIM. The plumber can't do BIM, maybe for his sprinkler lines. The drywall guy's not doing BIM. Or if they are, they're outsourcing it to someone who just does modeling, but they don't know how to build things. And BIM falls apart when industry doesn't hold projects accountable and project teams accountable for everyone doing it. And that's something that we can talk about this afternoon. In an ideal environment, everyone would do BIM. You could get rid of all the collisions and clashes. If you could have been a fly on a wall when this room was built, there were probably 30 or 40 hours of time spent saying, that's in the wrong place. Why did you put that there? This isn't here yet. Well, I didn't have the information, so I couldn't get it here on time. And that's what happens on construction sites every day, is those errors aggregate and get worse and worse. So what scanning and projection allows you to do is take a lot of that error out of the process. If you can create a workflow where you model what you want to build, you project how you want to build it, and you scan what you've built for QA/QC analysis to make sure that it's accurate. And so that was the process that we did. And in the shop environment, it worked really well because we can control the entire process. And that's where Greg comes into the picture. Greg is modeling the stringers, and then he's going downstairs, and there's Greg in the background, and he's working with Paul, and we would project the floor plate. Is it accurate? We would project the steel. Is it accurate? Now all the boxes that are going to hold the jig. Is it accurate? And so we could check our own work as we were going. And then what we did was we projected the lines for the stringers. So the guys on the shop didn't need to know this gets farther apart, and then it gets closer, and then it gets farther apart. We projected the lines for each of the pieces onto the assembly. And what Ryan was doing in the previous picture was using a pencil to mark what the laser had given us so that we could move the laser somewhere else. And all I need is the pencil line on the piece to be able to move forward. Where we tried to move laser projection to the project site, and we have the image of the KUKA robot in these. A KUKA robot was never used in the production of the Alliance Theater, as exciting as it sounds. But we tried to do the same thing in the field. So this is a laser scan of the structural slab and terraces of the theater that we're going to fill up with the millwork. And this is where this project ran into challenges. The concrete team was not working in BIM and didn't understand the complexity of the geometry. There was a disconnect with the structural engineer, and so we had slabs that were deflecting more than anticipated. And so laser scanning was great because it caught all of that. The problem was we're building all of these balconies while the concrete is being set. And so we're coming in, and these are 3D models of all the balconies that we've drawn and that we are building, and we're using laser projection so we know all of our balcony rails are accurate. And the problem is, and you can see it in the bottom of this image, the concrete slab is 8 inches away from where it's supposed to be. And so all the steel embeds in the slab that are supposed to hold all the balconies are 8 inches away from where they're supposed to be. And that's construction today. That is happening on every job site in the United States as we speak. The analogy that I use in a lot of presentations is you guys are I was trying to come up with a Ford GM electric car that would be appropriate, but I keep using the Tesla as the analogy. You guys are in a Tesla with your client in the back seat, and you're going about 80 miles an hour down the highway. And your technology allows you to draw 250,000 feet of ribs and create this wonderfully complex piece and environment. And CW Keller is in like the Ford Explorer Sport version. So we're in the middle lane, and we're doing our best to keep up. We're using Rhino, we're using Grasshopper, we're using lasers, but holy cow, we are barely keeping up with you guys in the left lane. And the rest of the construction industry is in the right lane, in the Caprice Classic. And they're looking over at the left lane going, you guys are crazy. And that comes out when we sat with the contractor to go through the models of this project, and the architect wasn't in the room. It was, have you seen this? This is crazy. They really think they want to build this. And that's the disconnect that happens in our industry. And if you don't recognize it, and you just get frustrated by it, you're going to conflict with construction. It's not going to go according to plan. And so your best bet is to embrace it. Your best bet is to meet Paul, whoever he is on your job site. The best person for you to meet on any project site is the site super. Don't worry about whoever owns the contracting company. The project manager is probably a nice person. Meet the site super, the person who's going to be on the job all day long, building your job with the plumber and the electrician and the concrete guy and the tradespeople, because that is going to be the person who is your conduit into what's working, what's not working. Is this going according to plan? And going back to that lifelong learning from mistakes. The concrete guys, this cost them, I think, about $250,000 to fix because it was their mistake. They were not building to tolerance. They had gotten themselves into a situation where the geometry was more complex than they were used to. And everyone's gung-ho in the beginning. This is going to be great. Well, I'll make it work out. The project was a year behind schedule because of all of the challenges with construction. So now you have a budget that's blown, a client that's frustrated, and an architect who ultimately got an amazing project. So this is what it looks like. Oh, I missed our field laser. So there's Greg in the field projecting walls and showing them that they're 3 inches off. You've got to make it work. And so we get in and we modify the balconies to fit around the concrete, and it all gets installed. And it's been open for a year, and it's certainly one of the projects that we're most proud of ever doing. But it could have been so much better. If there was a collaboration from the beginning that brought everybody together and didn't keep contractors at arm's length, and there was more trust and teamwork, the project would have been way more successful, probably closer to budget, and not so many compromises. And everyone made compromises to get the project completed. So, lessons learned. We have learned a lot of lessons over the course of the past almost 50 years. And so we were very fortunate right after that project to build the new Moynihan Station that needed lots of steam bending and lots of CNC machining. And so it was one of the first things we did when we talked with the design team was, let's not do what we just did. Let's fix and talk about what are the limitations. You can steam bend a piece of wood and keep it in the steamer for 2 or 3 hours. You can still break it. It's still just a piece of wood. It's going to expand and contract, and it's going to do its thing. So let's understand the geometry that you're trying to achieve, and let's take those lessons that we've learned and apply them to a fabrication process. And then for us, how do we move Paul away from hand bending every piece and starting to create jigs and automation that allow us to pneumatically bend and allow us to use cable systems to bend? Because in this case, we're doing a lot of repeat fabrication. And so that's what you're seeing in these images. These are 2 jigs that were built to be able to laminate, and we were taking steam bent walnut, laminating it to create an assembly, bending it, and then coming back and CNC machining it. So as I said in the beginning, I've gone way off my notes. So I'm going to catch up because I know that we're going to get into some new projects here, and I want a couple things that I want to make sure that I cover. Perfect. Okay. So this is Penn Station, or Moynihan Station. It is the expansion of Penn Station in New York City that was just recently opened. It was a 7-year project. Skanska was the general contractor. A number of different architecture firms contributed to it. We were working for a firm called Rockwell Group. And 6 months before it was scheduled to open, Amtrak decided that they didn't like the design of the seating area and wanted to come up with a new design. And so when we were approached to work on the project, and I was mentioning the lessons learned, it really did become a true collaboration. Client had a defined, we are opening Moynihan Station on this date. It was like December 14th. It doesn't matter what happens. You have to be done. And so we were able to work very closely with the project team to build in the rules that would allow us to be successful in fabricating this interior environment of benches and wall systems. And it became a true collaboration between everybody, the upholsterer, the AV team, the glazing team, the lighting team. If we didn't all work hand in hand and one of us fell down, then this wasn't going to open on time. And that would have been, I'll call it a financially painful process for all of us. And so what happened was the design team set the tone at the beginning of the project, and I mentioned it earlier, which was we trust everybody in this room to be the people who are going to help us get this thing built. And so you need to tell us when we're doing something that's working or when we're making a decision that's going to jeopardize the success of the project. And the most successful projects that we've ever been involved in are when the designer, and sometimes the client, but it's usually the designer, sets that tone. The tone from the outset is collaboration. The owner goes along and is like, oh, this must be the way you do it. You collaborate. When you set the tone of, oh, the contractor is taking advantage of us, or this isn't working, or that's not working, then it becomes confrontational. And on long projects, that confrontation can go on for years. And as I mentioned earlier, it doesn't lead to success. The rest of my images are just going to talk about some lessons learned, and then I didn't keep track of time, so. Okay, so I'm going to keep talking, but I do want to encourage you guys to ask questions, because I'll just keep talking and talking and talking. As we evolved from being a millwork fabricator to getting involved in more substantial projects, one of the lessons that we learned early on was understanding we need to know structural engineering. And structural engineering for us used to be, well, just glue more wood together and add more screws and it'll be fine. What do we have to worry about? It's a bench. When we get into projects where we have a 10,000-pound cantilevered screen over a staircase, structural engineering becomes a big deal. And lessons that we've learned over the years are, who knows what stair harmonics are? So stair harmonics are when everybody starts going up the stairs at the same time, and they're all stepping at the same time. And so your stair starts to move, and it can build a harmonic where the entire stair is moving. And so structural engineers have to design in for harmonics. When you attach a screen system to a stair, and you don't have the structural engineer who designed the screen system talking to the structural engineer who designed the staircase, you start to create problems with stair harmonics. And so, lesson learned, you have to collaborate. There could be 2 or 3 structural engineers on a project. If they aren't talking to each other, and we're all working in a vacuum, then we start to create problems for each other. And so it goes back to that same thing. Have you created a team that is open and willing to collaborate with each other? Ultimately, we solve the stair harmonics by just adding more steel plate to the stair, and you make it go away. But again, client paid for it. Architect didn't feel so great about having a change order, and it didn't need to happen. It would have been a phone call in the beginning of the process. Hey, you're attaching to us. What's that going to do? So lesson learned. This was a fun project that we recently completed where I want to encourage you to think about everything that is above this ceiling. You know, you're going to design jobs and you're going to be like, well, the ceiling's too low. I want to push the ceiling up. There's so much stuff above this ceiling that you've got to contend with. And so when you acknowledge that it's there and allow it to be there and start to design surfaces around it, then you make everybody's life easier. You make your project more cost effective. And so these are two examples of projects that were reacting to existing conditions to develop surfaces that just let the stuff be there and work around it as opposed to fighting against it. And so this is a project that we did in Oakland, California, where the team wanted to create this pixelated surface. And there was a ton of stuff in that area where you can see that it's a deep drop in the ceiling. And so they developed a control surface that went around that, offset their design up to like 6 inches below the worst case scenario. And no one walking through this lobby would ever think, well, why does that part drop down? It's obvious that it was part of the design. And that's the aesthetic that was presented to the client, and they love it, and it's a very seamless process. This next one's a better one because it was a much tighter assembly. So this is a restaurant in New York City that is in the basement of a building. And so this structural slab is already low, and you have to have ventilation and sprinkler and all of these things above the ceiling. And so the design team did the exact same thing. We went in and we scanned all that stuff, left it where it was, and they built a surface that worked around it, and then we built a system of slats that just compensated for it. So again, collaborating and working within something as opposed to rip it all out. I want you to move it all out of the way. All those things can be done. But I think designs are more successful when they solve for something like that more creatively than let's just throw money at this problem and move that stuff out of the way. Some people in the room will know what an Ephesus panel is. So an Ephesus panel is something that was very popular, I think, in the 80s. And it was the way they clad the outside of thousands of buildings around the country. It's essentially EPS foam skinned with stucco. And the problem with Ephesus panels was that water would get between the foam and the stucco would fall off. And so you had all these building facades that had these massive failures, and so Ephesus panels kind of went away. And so this was a great example of a project where someone who knew what an Ephesus panel was and remembered it and was older and had that in their brain was able to bring a suggestion to a project team that was trying to create a very complex precast concrete assembly in a space at Harvard University. And the issue that we ran into with precast was to make a precast panel, you have to make a mold, and then you cast the concrete in it, and you have the panel, and then you throw the mold away. And so you're kind of doing the project twice. The other issue with precast is that it's really heavy, and so you have to get a lot of structure. And so this was a great example of what about if you just make a foam panel and let's clad it with, in this case, fiberglass reinforced plaster. So technology has evolved. We're not the outside of a building. Let's take something that's old, that used to work really well except for this one water problem, and let's use it to create a really sculptural ceiling assembly at half the cost. Because we didn't have any molds to make, so we didn't have to make molds and throw them away and cast panels. We just machined foam and skin it with fiberglass reinforced plaster. And you get the same durability as concrete. And so you're kind of, there was 5 or 6 people that all contributed to that solution, all coming from different backgrounds. And we never would have got there if it wasn't an example of a project team that was open to collaborating with each other. Okay, I think. So the last 2 things we're going to talk about are staircases and then cast in place concrete. The workflow of engineering and integrating trades, structural steel, millwork, composites, and Corian, all work best when we start to bring the ownership of all those pieces and parts under, I'll call it a concentrated umbrella. We don't make the steel staircase, but we engineer the steel staircase. We don't install it, but we hire the installation team. And you're going to see this more and more in the industry. I started when we started the conversation about specialization. Staircases have become a place, as cast-in-place concrete has become a place, where companies like ours, and there are 100 examples of other companies that specialize in other things, and I say all this because I encourage you to go find those companies. Corastone, Zahner, there are fabricators out there that are doing really amazing things because they've gotten good at collaborating with a core group of people that allow you to roll steel plate and drop it through the roof of a house and then clad it with thermoformed corian to create a 2-story staircase. And there's a dozen companies involved in the execution of that, but all under one engineering umbrella. And what we're doing there is we're compensating for where BIM currently falls down. If the BIM process worked, then you could hire 5, 7 different contractors, and we would all do our model, and we would all come together seamlessly in the field. Until that happens, you need to find companies that are going to aggregate that process and own the model. And that's something that you really want to hold your contractors accountable for, is their responsibility is to either own the model or find people who can do that for them. So this is an example of a project where we don't entirely trust ourselves. So this is a staircase that was built in a high-rise in Manhattan, and so we had to bring the entire thing up in pieces in a small elevator. And so we have a challenge of having to field assemble structural steel. So the first one was easy. Build the whole thing and drop it through the roof in one big piece, and you're done. This one, you have to build the whole thing and then torch it all apart, and then put it in a tiny little elevator and bring it up to the 42nd floor and then weld it all back together. And so to ensure that that was going to work, we modeled the steel, we laser scanned the environment, we built the stair in our shop, and then we laser scanned the steel before we cut it up, and we put all of those models together. So the image on the left is the scanned space without the stair. The image in the middle is the scanned stair in our shop on top of the scan of the space, and then the image on the right is the fabrication tolerance model on top of all three. And all we're doing there is trying to avoid, the spiral didn't work, it's off by an inch. What are we going to do? It's on the 42nd floor of this building, and the welders are ready to go, and they're $200 an hour. It is a workflow that works very well as an internal check and balance of process. And so that's that piece put together. And then the images of it completed. So I will end here on the Miami Science Museum, and then please ask me questions. Miami Science Museum was the first large-scale cast-in-place concrete form system that our team was involved with. And as I've explained to you over the discussion, we're essentially a millwork fabricator. We're a company that builds custom interiors and theaters, and we work in wood and fiberglass and composites. And we were asked about 10 years ago to come to a meeting. It was in Boston, and you can see it on the website. It's called the Harbor Park Pavilion. And it was a project where the design team had created these very sculptural canopies that were going to be cast in place concrete. And the concrete team had no computer skill ability to create a form system, or fabrication ability to create a form system to create these complex canopies. And so we were asked to come to the meeting, and what they were going to do to start was they were going to take cut sections through their model, and they were going to plot on paper 40-foot long sections in 1-foot increments. And they were going to bring the paper to the job site, and they were going to cut plywood out with a jigsaw by hand. And that's something that the concrete industry does today, because it is back to the analogy of they're going 55 in the right-hand lane, and it's just working for them. We'll just throw more manpower at the project site, and we'll just do this all by hand. And so once we understood that you just need us to cut some plywood out, and it's going to be curved, and then you can build this canopy, it really opened up a whole new world for us in cast-in-place concrete form fabrication. And so this is a project that we did for the Miami Science Museum. It's a 135-foot diameter, 35-foot deep, cast-in-place concrete fish tank. You stand underneath it, and you look up through an acrylic lens. And so we adopted what we call the IKEA version of concrete form systems. The challenge was, we're in New Hampshire, and this project's in Miami. And the tank is so big, if we pre-assemble all of these forms, I think we're going to need about 60 tractor trailers to be able to send the forms down to the job site. And so we worked with the team to develop a form strategy. So this is an image of the forms that we built. And we literally went and got IKEA instruction manuals, and we looked at, well, what do? They essentially create an exploded view of what they're going to build, and they don't put a lot of dimensions on it, they don't put a lot of notes on it, they create a visual to put the piece together. And so we did the same thing. We said, we're going to have 17,000 unique parts that are going to get machined, and we're going to label them, and they're all going to be directional, and they all only go in one spot, and we're going to shrink wrap the bundle together, and we're going to ship it to Miami, and the team in Miami will take these bundles and lay them out and just screw them together. And that's why IKEA is so successful. It works. Forms were assembled on the job site and craned into place. Similar, we had to build a 3D model of the concrete, we had to build a 3D model of the form system, we had to build a 3D model of the shoring system and bring those all together. We had 3 structural engineers because no one wanted to take responsibility at the end for the liability. We joked, Matt Johnson, who Katie knows, when we engineered the form system, we had to compensate for 1 million pounds of rebar and 6 months of live load of people climbing around on the forms, installing the rebar. And so the joke was, when they go to pour the concrete, we're going to have a rental car in the parking lot. Because if it goes south, we are getting in that car and we are driving off into the sunset, and no one will ever see us again. It was one continuous concrete pour. There were 101 concrete trucks, and they poured for 28 hours straight and created the aquarium tank, which you see there. I'll end there. That was a good way to end. Leave the shark up on the image. Questions for me? I've done all the talking. And I know everyone's shy, so I'll just start pointing to people and asking them questions. Or I'll just keep calling on Katie. Not a... Thanks, Carl. You'll be the icebreaker.
Well, you're clearly not the mill workshop.
Nope.
Like 3 or 4 questions, but maybe one to get started, because it actually seems like from the first project that you showed, the theater, architects had a whole bunch of time to be working in isolation, and that didn't serve them well. It almost seems like there's a liberating quality where a certain point where it's like they're working and working and working. Okay, all those rules have to go out. We have to come together collectively as a team. I think there's a pretty amazing aspect to that where it wasn't business as usual at that.
It couldn't be. The project would never have been done on time if that, I'll call it that traditional process of go and do 100 pages of drawings and draw all the details and try to figure out how you build this, that, and the other thing. That's the way it used to work. Our architects used to produce huge drawing sets, and they figured out every detail, and contractors just built what was in the drawings. But there's a lot of contributing factors to why that doesn't work anymore. The main one is you're not getting paid to do that anymore. Your client isn't willing to pay you to draw cabinet sections or the form system. When we get the drawings of the tank, there are no drawings of the forms. It's just a drawing of the tank. And you figure out the forms. And the reality is specialization and the pace that projects move don't give you the luxury of doing those drawings and getting paid for them. The other challenge is it's become so complicated that you can spend a lifetime trying to understand all of, and I'm showing you a sliver of the construction world. It's just our little tiny piece of the pie. Go into facade construction, go into bridge construction or infrastructure construction. It's a whole different set of rules. You have to build the collaborative process to be successful on these projects.
And the staircase that you showed is maybe somewhat analogous. The way that I understand it, there's whether or not it's a bid model or anything that exists for the rest of the project, as long as it says, and then that allows you as a team, build a team, set your own rules for that independent and sequestered thing that's going to happen, be staircase, tank,
Yep.
whatever it is, and create a kind of microcosm of the entire industry. How does that change with the contract or the way that you build that team?
I would say that's a lot of our work, and it's that 10 or 20 architects that we work with over and over and over again are coming to us very early in the design of the staircase and saying, we want you to own what's in this envelope, in this rectangle. And so it allows us to take the same people that we do that work with, and we've gotten good at it, and we do it together a lot, and collaborate to make that successful, and do it quickly and cost effectively. Two things that I'll say to it, and this would have been one of my notes that I probably skipped over early on: tolerance. Doesn't matter how much time you spend laser scanning and how much time you spend laser projecting and how good your 3D model is, you have to know that you need tolerance. Humans, at the end of the day, frame this wall and it's probably 1/4 of an inch out of plumb, or this room is probably 2 inches narrower than it was designed to be. And that happens everywhere. And if you think that the built environment is going to be to the same level of tolerance as your model, you're in for an uncomfortable awakening. It never happens. Even in the shop environment, we have tolerance. Tolerance is in just, I'm tired at the end of the day, and so I didn't pay close enough attention to my tape measure, and I marked 5/16 instead of 5/8. Tolerance is also buildings move. I talked about stair harmonics. Stairs shake. Wood expands and contracts. When we started the Alliance Theater, one of the first things the client said was, do we need to put humidification and humidity controls into this environment because it's going to be so much wood? And we said, no. It doesn't matter what you do. The wood is going to move anyway. It's going to expand and contract. You can't control that. So don't try. Let's just let it do what it's going to do, and build in details and build in a system that allows it to do what it's going to do. And that goes back to that compromise. I can't think of how many times we've been in meetings where we're being told, well, just do something so that it doesn't expand and contract. Can you just put more finish on it and then it won't absorb humidity? No, it doesn't work that way. So learn that and accept it, and then build an understanding of that into your projects and into your designs. And that's where you'll be more successful. Yeah?
For the theater, the space for now, like really guys in plant, you get a lot of sound back on the spaces between wood.
I would say that, and I'm not the acoustician, but they did do a lot of testing after it was complete. And and this is anecdotal, I'd say they probably got 90% of the way there. Acoustics are really basically, it's transparency. We want the sound to pass through what it's going to hit, or we want it to reflect, or something in between. And there's all different gradients. We want it to reflect, but not too much. And so some of the ceiling panels that we built, there was that one image of the 5-axis machined part. You know, those parts were about 8 inches thick and had a rubber membrane on the back of them so that they would be much denser as an assembly. And so there's a lot of work that goes into studying what all of those surfaces are going to do. But when you start to make compromises on this panel is 3 inches further forward than we thought it was going to be because the concrete's in the way, and we're not going to cut all the concrete out at this point, those compromises have to be made. So is it acoustically perfect? No. No, probably not. Can it be? Probably not. Oh.
I was just going to ask, do you foresee use of
Uniform in the sense that it's getting consolidated under smaller umbrella of software platforms, yes. There's only a handful that'll kind of make it through, and some of the smaller companies that are more unique start to fall away. And larger general contractors have to embrace it. Every contract that we receive has a BIM section, like this is what you have to do as part of your contract. The challenge is, like I mentioned, if you're a smaller AV company, you don't have an engineer on your staff who can do 3D modeling. You can't afford to have an engineer on your staff who does 3D modeling. So how do you contractually participate to that BIM process? A lot of times they just don't. So everyone gets contracted to do BIM, but there's no penalty for not doing it because ultimately the client's not holding people accountable for doing it. And this becomes a big debate that we have with general contractors. And we've gotten to the point where we write provisions into our contracts that say, we're going to do the BIM process as you've defined it. But if everyone else doesn't, that's going to make our jobs a lot harder. It's going to cost you more money. So the challenge is that they can't find subcontractors who all have engineers on staff who can model everything that they're going to build. That's expensive. So it is a tug of war. Certain projects are better. Will it be fully adopted at a certain scale? Yes. You start to get into projects that are $25 million, $50 million or more as an entire project cost, then it becomes more standardized. Universities are good at standardizing and holding accountable. Municipalities, if you're doing work for Moynihan Station, then yeah, you have to do it. But if you're just doing an office project or a residential project, chances are it's not going to be very uniform.
So Subi is one of our alum adjunct faculty members, and who also is a computational designer with a local firm. He asks, a huge part of trust has to do with the easy transfer of data from design to fabrication. How much of the author's data / model do you implement, or do you always start from scratch?
We always want the design team's model. And
Just one over another architect by saying that.
you've done all the work to model the project. Sharing it with us gives us a huge advantage in the starting point of understanding your project. The Alliance Theater is a great example. Trahan had modeled all those surface areas and had modeled all of the stringers. We couldn't build from it, but we could go into that model and measure surface area, and we could measure linear footage so that we could start to build the cost of the project. To bid that project, it's how much wood do we have to buy? 250,000 feet. Okay, how much does it cost? $3 a foot. Okay, there's a great metric. Here's all your wood, and this is how much it costs. We rarely are allowed to, and most times have to sign a waiver that says we will not build from the design team's model. And that goes to liability. And that's a whole day-long presentation in what we call risk delegation. An architect is hired to design something, and as an architect, you carry professional liability insurance that essentially says if you screw up, you have an insurance policy. Well, what happens is when you start to delegate the design assist, delegated design, design build, you're starting to shift that responsibility and liability onto a fabricator. So we now carry professional liability insurance. General contractors carry professional liability insurance. And so what the architect is saying is, I've not figured this out. You're going to figure it out. I'm delegating the design to you, and you are going to figure it out. And so we therefore then build the 3D model from scratch using the information that we've received. We're not going to change it. It's a great starting point, but we're going to rebuild it as a fabrication tolerance model because we own the liability at that point of the project not falling apart. I wish I had some. We are doing this thing that no one's ever heard of. A lot of what we're doing, and it's a little bit more mundane as we've grown, is process workflow. We're 111 people across 2 facilities. We have project managers that are remote to our operations. So we have a project manager in California, one in Connecticut. We have people who work remote just because that's the way the world has gone recently. And then we have people in the shop who are building. And so how do we stitch that entire workforce together and engineer and procure materials and field survey and build? And a lot of that has been through building the infrastructure of a larger company so that we can become a larger company. And that's been a lot of our fundamentals. We kind of grew very organically following the path of a lot of these projects. And that was great until we got to a certain scale, but then we had to put our big boy pants on and be like, okay, we got to become a bigger company because of things like risk delegation and liability and contracts and legal and structural engineering. Innovation that we see in the industry, in the people that are doing complex BIM coordination, it is amazing because you can create a BIM environment that is so robust that you don't need to go to the project site. And as laser scanning has become, like we 10 years ago bought our own laser scanner, and it was this huge investment, and we saw the benefits of having it right out of the gate. You can now call, and I'm going to make up the name of the company, lasers.com, and get your project laser scanned for $1,000. And you don't need to buy it anymore. And so what we're starting to see is construction teams implementing laser scanning as part of their workflow so that we don't need to go and scan ourselves, we don't need to measure ourselves, it's part of the process. And everyone is getting the benefit of something that was very, I'll call it proprietary or unique to a certain number of companies early on. I can speak to what I know some other companies are doing that are things that we'd love to adopt, which is as you're building projects, there's technology out there that allows you to place things on things that are in space, that are in very random complex orientations. A lot of facade companies are doing this. And it's constantly providing live data back to the fabrication model of what's going on around that thing and construction that's going on. And a lot of what happens in a big building is you build, or this happens in bridge construction, you don't build the bridge to be what it's going to be when everyone is on it. You build it with what's called camber or deflection, because you have to compensate for the weight of the bridge settling itself. And so understanding how concrete settles, understanding how steel, when you put a high-rise together, is moving, and having connections to that building that are live and giving you live feedback on what's going on as that weight is added, as that construction is happening, is something that becomes very proactive as opposed to reactive. You know, everything I showed you was reactive. Let's build it, scan it, and react to it. This is really giving you kind of a live feed on the evolution of that construction. Material innovations for us are definitely in composites. There's a lot of work going on as we understand materials that you can thermoform, materials that you can cast. Ductile, if you're familiar with SCC, so self-consolidating concrete, is a product that's used a lot in Europe and is making a foothold here in the States. We've bid on the facade for the Obama Presidential Center, which is an 80-foot tall cast in place, precast concrete speech. So it's one of Obama's speeches that is in 6-foot tall letters that wraps the outside of the facade, and that would all be done in ductile. So there's no structural reinforcement in the concrete. You know, traditional concrete is going to have steel rebar. Ductile uses micro stainless steel fiber or micro organic fiber to essentially create a matrix inside the material that is essentially structural, eliminating the need for rebar. So as advances in fabrication for complexity of forms keeps up with innovations in the products that can be used to cast and create structures, that to us is a very exciting place that we see things happening in the future.
So I know that you're bidding on a project in Detroit. I'm certainly hopeful that you get it. I'm sure us too. Before we thank Shawn for being with us, I just want to make an offer. We like to, when people come to campus, Shawn is going to be staying at the Affleck House. We like to take a group of about 8 or 10 students and faculty to have dinner. And so if anyone is available at 6 p.m. tonight, if you're interested in joining for a kind of more intimate dinner conversation with Shawn, please sign up with Andrea. Okay? These are really great opportunities that we have. So let's give Shawn a round of applause. Thank you so much. How many of you were in Lauren and Sarah's class? All right. Well, Shawn hasn't had a chance to eat anything yet, so we're going to take a couple minutes and then we'll join you in A210 in probably like 10-15 minutes. Right? You guys start at 2, right? Yeah. Okay, so we'll see you in a few minutes. Thank you, everybody, for coming.